Alright guys, so let's do an example for Bernoulli's effect, or Bernoulli's equation, using Bernoulli's equation, okay? So, oh, just a moment, I give you guys the other one. Okay, so here is the one that I wanted to show you guys. Alright, so this question goes like this. So here is a water tank here. So the question says, a gunfight breaks out near the town water tank. The tank is open at the top. One of the bullets make a small hole in the tank, half a meter below the water level in the tank. Find the speed water exits the hole in tank. Okay, so let's try to make this, let's try to do this. So the first step in doing physics problem is what? Writing down what is given here. Given information are so something there like a height h is given as 0.5 meter, right? Half meter. We also want to make the tank is open at the top, so let's make a diagram. Okay, I'm gonna put this over here, make a diagram and remove this thing. So let's make a tank here, and then tank here. Oops, I'm gonna make all big tank here. Okay, it has an open top. Okay, so I'm gonna make a top. It says open top. Oops, this is just the open top. Okay, here, which means what? Here, P naught, right? The pressure is P naught is really P atm, atmospheric pressure over here. Okay, if it's open. And then it has a, assuming it has the, water all the way up here. And then, so this is water, and then there is a hole after, the tank, guns are heated. So from this hole, the water is going to flow, okay? Now, how do we, so what else is given here? A small hole makes tank half meter below the water level in the tank. Find the speed water exits the hole in tank. So what's the speed V equal to what when the water is flowing away from here? So maybe we need to take some point here, right? The cross-sectional area, some A, okay? And then find the speed at which this water is flowing through here. Now, so let's write V. Let's make a coordinate here, okay? So let's give this as our origin here. Let's make a y-axis here. And then let's say this point, through which the point that corresponds to this hole, let's call this as our y1, okay? And then let's call this the top region. The water is all the way up here, right? Like it's fell. And then that height, this height as y2, and then this difference is what given to us. Okay, so y2, this height, right? y2 minus y1 is what is given to us, and that is our height h, which is 0.5 meter. Okay, now let's call this as our point 1, just labeling here point 1, and then this as our point 2 here, just labeling. Okay, so what is our V1? That's the question. Now, from Bernoulli's equation, before we apply Bernoulli's equation, what is important here is, do you think this water, what is the speed of the water when it's flowing? So if it is our point 1, it is flowing at some speed V. The tube is really, this hole is small, so it must be, the water must be exiting at a really high speed over there in comparison to the speed over here, right? So, but then this tank is so big, it is a really large tank, and this hole is so tiny. So the water must be flowing from this, in this portion. When it's going down, it must be going slowly, because the cross-sectional area is so large, right? So from continuity equation, right? So since A, you know, A times V, A times speed V is constant, or you could also say, you know, fluid flow rate. When this area is really large, this V must be really small, okay? So what we are going to do is for point 2, we are going to ignore that speed of the water. Assume it's really moving at negligible speed. So we are going to write that as 0, okay? Alright guys, so let's go ahead and then you apply Bernoulli's equation here. So from Bernoulli's equation, we can write, let's call pressure at this point as P1, it's outside here, this point also as this P2, okay, that's outside, it's on the top, okay, and then P2 over here. So let's write the Bernoulli's equation first. So we have P1 plus half rho B1 square plus rho G Y1 must be equal to P2 plus half rho, I'm going to take this away guys, rho B2 square plus rho ZY2. Now note, because this pressure we are talking is, it's on the side, right, like the water front of the water, and this is on the top, this part is really facing towards the air, okay, the water is trying to come out, right? So the pressure over there and the pressure here are the same, equal to atmospheric pressure. So this P1 is just P atmospheric pressure, or P naught we can write, plus half rho B1 square. Let's do this guys, see, rho ZY1, rho ZY2, okay? So we are given what, y2 minus y1 is 8, so I'm going to take this guy over here, okay? So take this 2 over that way, and then write whatever we have, and then so equal to, right, I'm taking this over there, okay? So I need to remember that in a minute. So P2 is again equal to atmospheric pressure, PATM, plus this V2, we said, because the water is moving really slowly, so this quantity here is negligible, 0, okay? At point 2, the water is moving so slow, we can ignore the speed, so that is just 0. And then we have this rho ZY2, we do need to remember to bring it back here, minus rho ZY1, okay? Now, here really, instead of writing the other thing, so let's cancel these guys out, and then let's do this. I'm gonna just isolate this B1, and then let's do this. Let's not leave this space. Half rho B1 square equal to rho Z Y2 minus Y1, but this Y2 minus Y1 is really H, right? So this is really just rho GH, okay? Now, let's isolate B1, so we have B1 equal to, this guy should go to that direction, right? So 2 goes up and multiply, 2 rho times Z times H, and then, oh actually we can also cancel this rho and rho, we don't need to write that down, you don't have to write it down. So this rho and rho can also be cancelled, so 2 goes up there, 2 times ZH, and then this, because this was E square, when we take that E square to this side, it becomes E square root, so we have that. B1 equal to E square root of 2 times Z times H, okay? So this equation is called Torricelli's equation. This gives the relationship between the speed of the fluid at which the speed is flowing with the height, okay? So now please look at this. We have everything, right? We know what is the value of it, we know what's the value of G. This is just acceleration due to gravity. Just substitute that and please find that out, okay? So if we do that, next step is what, B1 equal to square root of 2 times 9.8 times 0.5. What do we get here? So please do that calculation. So what does this give you? 3 point, about what, 2.113 meter, okay, per second. So look at this. This is the speed. This is pretty high speed, right? For the fluid to flow through there, that's 3.13 meter per second. In 1 second, it's going. 1 meter is about this. It's going about 3 times of this in 1 second. Okay, so that's pretty large. So this is an example of a Bernoulli's equation. Please practice some examples from your own textbook. You don't even need to go to the whole, exercise section. Just try on your own to, do the problem that's given under the examples. Try to just solve it. Try it on your own at first. And then if you are not able to, go back and look at how it is done in the textbook also. So that way you get to practice more problems. Okay, so here is one example. If you do one more example from textbook, that will be very helpful for you. Alright, let me check my video whether it's recording or not. Okay, so that is still, it is still recording a video. So oh, this is, I think, alright, this one I'm gonna just write this down here. This is not in your, it's not posted in your class lecture overhead, so this is only here, okay, on the board. So let's look at a conceptual question. Alright, so let us look at one more. This question is actually there on your class overhead, but the other question I'm going to write in 2 minutes, it's not. Okay, so let's look at this one first, and then we'll go back to that. Okay, so here is a conceptual question. Water is flowing down through the pipe shown in the drawing. So here is a drawing. We have point A is at the higher elevation, while point B and C are at the same elevation. Rank the pressure at the 3 points. Largest first. So, where do you think the pressure is largest? And then rank the pressure. Where do you think the pressure is largest? Rank the pressures according to, the magnitude. So basically, highest first, then the second one, and the third one. Okay. And then you are given a helpful equation here. So AV equal to constant, right? Volume flow rate, and then you are also given a Bernoulli's equation. So please try to think about it for a minute and see if you can come up with the answer. Please, when you see, I know I'm teaching this through video, but when you are doing it, you should definitely sit there with the notebook, or maybe your, digital notebook or something, so you can draw this diagram and then try to work on this, okay? Because that's the way physics work. You cannot just sit there, watch, and then, do something, and then after, like, 10 minutes you forget what you did because it's not written, and then your mind, it's like mind will kind of like, not remember. I mean, you may remember it, but at least in my experience, it is more helpful to just write this down and do this problem. Okay, so take a minute or two and then try to come up with the answer. Alright guys, so let's look at first. Let's look at this, using continuity equation or volume flow rate here. A times B is constant. So let's look at in point A, point B and point C in terms of area. Point A and B, they have the same cross-sectional area here and here, right? So it's kind of, it goes something like this, and then we have something like this, and then it goes like this. So oops, like this, right? So point A has cross-sectional area something like this, point B has cross-sectional area like this. This is A, this is B, and then point C has cross-sectional area something like this. So at point C, of course the cross-sectional area of the C is greater than area of the B is equal to area of A, right? So these two areas are equal, but at point C it is much bigger, which means speed of the fluid must be very small here in this wider region than in these two regions, right? So in these two regions the speed is constant, right? Now next step is what now? What happens about the pressure? So if the speed is really small here, what happens to the pressure, guys? Where is my eraser? So look at the pressure here, okay? So the pressure, because the speed is so small, right? And this point, it is at the same height. So the pressure here is what? Must be the greatest, right? Even though it's at the same height, however, because the speed is so small, so the pressure is high here. And then this is at some pressure, right? It has some value of pressure here, and then this is at a different height, okay? So because this is at a larger height, so pressure must be greater here. So oops, sorry about that. So here, right, so the pressure here is at point C must be greater than pressure at point B, right? Okay? And then pressure, because it's at a higher depth than this guy here, right? And then pressure at point A is the smallest one, okay? So this is the conceptual question for Bernoulli's equation. Let me check this video. Okay, so I got another 4 minutes that I can, this camera will keep shooting this video. So I think we can do this. Let's see. Alright, so the conceptual question is this here, guys. So I'm going to make this here diagram. So it got some deposit here, okay? There is this thing. Here is some deposit, and then this says deposit. And then this small thing here is a hemoglobin molecule, okay? So this is a hemoglobin molecule. So the question reads like this. Blood flows through a coronary artery that is partially blocked by deposits along the artery wall. So we have a, blood flows through here, but then this is the artery wall and there are these deposits on the wall, okay? Now the question is this. Number one, through which part of the artery is the volume flow rate largest? Through a, you see this is a wider, here is a narrow, right? So option is A, narrow part, B, wide part, C, same in both parts. Okay, so again I'm going to read this question. Okay, through which part of the artery is the volume flow rate largest? Which part do you think is the largest? Narrow part, through the large part, or same in both parts? So if you remember, volume flow rate is what? Q equal to A times speed V, right? So it doesn't really matter, right? We know as the if area increases, what happens? Speed decreases. If speed increases, area decreases. I mean, if speed is larger in a smaller area. So this is a constant quantity, so must be same in both, okay? Number 2. I'm gonna just, okay, so same in both parts, alright? I'm gonna erase this because I want to use the same option and I don't want to keep writing again. Alright. Number 2, through which part is the flow speed greatest? Options are narrow part, wide part, same in both parts. So it's talking about the flow speed, okay? Speed of flow, okay? So through which part is the flow speed greatest? Narrow part, wide part, same in both. You guys already know this, right? Greatest means it has to be through the narrow part, okay? Alright? And the last question is, if this one is not recorded on video, please ignore this, okay? If it is recorded, that's fine. Number 3, a hemoglobin molecules moves from the narrow region into the wider region. What happens to the pressure acting on the molecule? So the molecule is moving from narrow region into wider region. What happens to the pressure acting on the molecule? Pressure options are given to you. A, pressure and increase in pressure,